All right, so welcome to this session on Unreal Insights and performance optimization. My name is Ken Kuwano and I'm a lead software engineer at Epic Games Japan. In this talk, we will walk you through how to approach performance analysis in game development and how to use Unreal Insights to identify and resolve the performance issues effectively. By the end of this session, I hope you will have a deeper understanding of Unreal Engine and Unreal Insights and feel confident tackling performance bottlenecks in your own project. Here's what we'll be covering today. We'll begin by understanding what performance issues actually are and how they relate to Unreal Engine's underlying architecture. In this first half of this session, we will take a step-by-step look at how to analyze the performance using Unreal Insights. Then, in the second half, we will dig into more complex scenarios. Let's get started with section 1. In this part, I'll explain how games work under the hood, introduce Unreal Engine's architecture, and give you a clear picture of the performance challenges we typically encounter. But first, let's briefly revisit what we mean by performance issues. Let's begin with a quick question. When you hear the phrase performance issues, what kind of situation comes to mind? I define a performance issue as a state where the game cannot maintain a stable, playable frame rate. Does that match your expectation? Let's take a look at a concrete example of good performance. This video shows a scenario where there are no performance issues. Okay, so as you can see, the character is moving smoothly at 120 FPS, but I'm sorry, so I recorded the setting to 60 FPS. But it's okay, with no visible hitching or slowdown. Now let's look at the scenario where performance issues are present. We'll start with the example on the left. Here the character moves sluggishly. This is an example of hitching. Now take a look at the screen on the right. At first glance, the movement appears smoothly, but at times the screen seems to freeze. This is an example of frame drops. These momentary delays, hitches, or frame drops can negatively impact playability and should be identified and resolved before release. Performance issues like these need to be addressed through optimization. Optimizing performance enables us to deliver smooth and responsive gameplay. From a development perspective, optimization helps prevent crashes, shorten the load time, and speed up debugging and iteration. For all these reasons, performance optimization is essential. So what can we actually do to improve performance? That's right. The first step is to use start unit command. That gives you a quick overview of the performance characteristics of your project. Pay attention to the values that appear. They'll give you a rough idea of where potential bottlenecks might be. Start unit command displays several performance related values: frame, game, throw, RHT, and GPU. The details of each are shown in this table. This mainly represents the per frame processing time for each thread. For a title targeting 60 FPS, the time for each should stay within 16.6 milliseconds. On the other hand, if any of these values exceed 60.6 milliseconds, that means a performance issue is likely occurring. The item shown by start unit flow the data flow leading up to rendering. For example, imagine the player is using the controller to move a character. On the game thread, the input event is detected and the character's position is updated. Then, on the render thread, draw commands are generated for rendering. Those commands are passed to the RHS thread, where they are translated and finally sent to GPU. In this way, the character is rendered on screen through a flow from CPU to GPU. The previous diagram shows the data flow for a single frame, but in reality, a game runs as a continuous sequence of frames, so the timeline actually looks like this. This is a simplified explanation of the data flow and architecture. But since thread is the engine are processed in parallel, this gives a general idea of how things actually work. If a performance issue occurs somewhere, the timeline will show increased processing time for a specific thread or unit. As a result, rendering updates get delayed, and the output on screen is no longer updated smoothly. To address this kind of issue, we first needed to identify the general bottleneck. Then, at the next step, we use Unreal Insight to perform a more detailed performance analysis. So let's now begin section 2, basic analysis. So far, we reviewed common performance concerns in general terms. In this section, we explore how to investigate them using Unreal Insight. Our focus will be on 3 key areas: game thread, render thread, and GPU. For each, we'll cover what bottlenecks are likely to appear and how you can use the tool in Unreal Insight to uncover and address them effectively. Before diving into performance analysis, it's important to start with a proper trace capture. Unreal Insight uses the trace option to specify the data you want to track. And then there are various options such as embedded in such screenshots or bookmarks. Then more leverage your trace capture, your trace setup. The easier your analysis will be later. The captured data is then loaded into Unreal Insight to start analysis performance. It is important to understand the Unreal Insight UI for performance analysis. The Frames tab shows a bar chart of frame times for the entire trace session. You'll see tall bars where spikes or pitches occurred. This helps you quickly identify which frames were the slowest and where to begin your investigation. Next, go to the timer or counter tab. They list the events that run during the selected range and show how much time each one consumed. This helps you locate expensive or repeatedly executed functions, those that may be worth optimizing. The most important tool in Unreal Insight is the timing view. This is where you can see exactly what each thread was doing, frame by frame, around a shared timeline. Since Unreal is a highly multi-threaded engine, many bottlenecks are caused by synchronization between threads. Not just individual processing time, timing view lets you spot and diagnose those issues. The timing view shows multiple threads aligned horizontally, letting you compare their behavior across the same time span. By closely observing the relationships between threads, we can trace where performance bottlenecks are actually originating. Here's a simple approach to finding bottlenecks. First, source the frame list by drawing and find the slowest frame and zoom in on that time frame and look at the thread. Then find the thread with the longest processing bar and find the event marker that took the longest time. At this point, ignore markers such as idle time and wait for tasks as they are passive, delayed, and not active processing. Okay, so let's now begin examining the game thread in details. This thread is responsible for game logic. Because of its central role, it's often the first place performance problems arise. We'll walk through how to investigate this thread step by step. To profile the game thread effectively, use the following trace command. The named event flag is especially useful. It records named events like function calls. You can also add a channel like animation or net depending on what you want to analyze. This is a default timeline view when you open a capture. Start by scanning through the frames and identifying those with long processing time. Once you spot a slow frame, zoom into it to examine the details more closely. This is the first step toward pinpointing a performance issue. Once you identify a spike frame, zoom into the game thread to see what it was doing during the time. By examining each block in the timeline, you can uncover the actual operation that caused the throwing. As you zoom in further, look for individual events that are noticeable no longer than the others. These are your prime suspects, functions that significantly extend the frame's processing time. By identifying the longest marker within the thread, you can directly trace the core bottleneck. The core view located in the bottom right shows a hierarchical breakdown of function calls. It displays the call stack for selected time range, making it easy to trace which function called what and where the most time was spent. In the core view, hot icons appear in areas with significantly longer processing time. Start your investigation at these hotspots. This diagram simplifies the game thread activity across multiple threads. As you can see, frame 12 runs longer than the others. It continues processing all the way to the end. This clearly marks it was a bottleneck. Recognizing this pattern visually is a key skill in performance profiling. When you encounter game thread bottlenecks, there are two main strategies to optimize. First, reduce unnecessary game thread load. Eliminate redundant ticks, or convert blueprint logic into native code. Second, offload non-critical tasks to async threads. Things like sound processing or background tracing can run outside the main loop. Both approaches aim to shorten the timeline bar and ease main thread pressure. I won't go into full optimization methods today, but for those interested, this slide links to a previous Unreal Fest session that focused on game thread performance. This slide covered practical techniques and how to use insights for deeper analysis. So if you need to tune your game thread, this is a great place to start. When profiling the game thread, there are a few key things to keep in mind. First, we want to look for processing that's consistently taking a long time. This could be heavy logic that's triggered every frame or every tick. We also need to consider thread dependencies. If the game thread is just waiting for something else, like a worker thread or async loading thread, it may not be the actual bottleneck. So when you analyzing delays, don't assume the game thread is always to blame. It could just be stored by another part of the system. Now, let's take a look at the render thread. In my cases, the render threads ends up being the second most common bottlenecks right after game thread. Heavy or complex scenes lots of overdraw can all place serious strain on this thread. That's why it's critical to analyze it properly. To properly analyze the render thread, enable this channel in the thread. This will give you access to the entire rendering pipeline, including command submission and render graph activity. A long render thread time suggests that there are either too many drawing codes or render thread render command queue is bogged down. It is important to visualize each thread, each render path in detail to see exactly where the time is going. Okay, let's now look at the render thread. Using the familiar timing inset view. If you look at the upper section of this thread, you will notice some red birds. If you see spikes here, the next step is dig into the timing and isolate which threads are taking the most time. Here we are zoomed into frame 600. The game thread completed in 27.1 milliseconds, but the render thread took 51.9 milliseconds. That's a significant gap, and because of it, the game thread is the next frame. Frame 601 ends up stalling. If you look at the render thread processing, you actually see additional processing occurring. This is a textbook case of bottlenecks propagation across threads, where the render thread delays ripple back and affects the overall frame rate. This diagram illustrates the parallel relationship between game thread and the render thread. It shows that they run independently, but if one takes too long, the other may still be blocked indirectly. You can see that the render thread is delayed in the area corresponding to frame 12. It's important to observe which threads are working and which are idle. This kind of embarrass tells us that the render threads need to be optimized, not just to speed itself up, but to allow other threads to progress effectively. The render thread sits directly upstream from GPU, so any delays here can ripple into GPU or RHS thread. To evaluate whether the bottlenecks lie on CPU or GPU side, we need to compare their processing time. If the render thread is taking longer than GPU, that suggests GPU is a limited factor. On the other hand, if GPU is the one running longer while the render thread has already finished, then the bottleneck is likely on GPU. The important thing is it's not just to look at one part in isolation, but to understand how the render thread, RHI, and the GPU are interacting. Okay, so now we come to the final component, GPU performance. Until now, we've focused on CPU bound threads, but rendering ultimately happens on GPU. Heavy post-processing, shadow passes, or writing complexity can all result in GPU bottlenecks that hurt frame rate. To profile the GPU, you can use the GPU channel or default channel. GPU analysis focused on identifying longer render passes. If needed, use a dedicated GPU profiler or debugger tool to go even deeper, especially when shader level analysis is required. Note that Accurate profiling of GPU requires that the rendering resolution be kept constant. For example, fixing dynamic resolution or screen percentage will measure performance at the target screen resolution. Also, if you want to measure the pure load of the rendering path, you should disable async compute using this console command. Let's also look at GPU tracing in Insight. The latest version in UE 5.6, the GPU profile has been overhauled. You can now visualize the graphics and the compute operation in a hierarchical timeline. This allows for much more intuitive analysis, even without relying on platform-specific tools. And if you select a track, you can also view the dependencies between the graphics part and the compute part. Let's explain what each state in the GPU timeline means. GPU work refers to the time GPU is actively rendering or computing, which should be high utilization. GPU wait means GPU is stopped, waiting for dependencies to finish. And idle means the GPU is completely inactive. This may happen when vsync is enabled or under right workload. But if too long, it means that the GPU is not feeding the GPU fast enough. Wait fence and signal fence are synchronization mechanisms used to coordinate work between different graphics and compute parts. Signal fence is used to indicate that work on one GPU queue is complete, while a wait fence pulls the GPU queue until the corresponding signal fence is processed. Therefore, to use the computer pipe effectively, you should also be aware of the dependencies between these fences. If you encounter a problem that cannot be identified by Insight, you can use these GPU profilers and the debuggers to identify the problem. You have several options on Windows platform, but you should use dedicated profiler tools on console platform. They allow you to examine each graphics resource and command in detail, debug shaders, and dig deeper into performance issues. Now, to conclude this chapter, let me briefly summarize what I have described so far. Game threads, render threads, and the GPU need to be optimized if they're bottlenecks themselves. But it's important to remember that the frame time is often shaped by a chain of dependencies. Game to render to RHA to GPU. Unreal Insights helps us to see how these stages connect and where each frame's delay originates. Use that visibility to guide your optimization efforts. Let's now move into section 3, advanced analysis. In the previous sections, we focused on individual threads and simple bottlenecks. Here, we'll deal with more complex performance problems, where multiple threads interact and overlap. We'll focus on two specific areas that often introduce subtle but significant issues, worker thread and file I/O. Let's begin with worker thread. This is where the advantages and pitfall of multi-threading collide, and where a lot of real-world performance issues tend to show up. To investigate worker thread behavior, use the trace command like this. This lets you see which tasks were executed on which thread, and how long they took. If heavy work gets concentrated on a few threads, the benefits of prioritization break down, and sometimes even the main thread gets blocked. Worker threads are used for multi-threading and come in two types, foreground and background threads. foreground workers run runtime sensitive tasks and can block the game thread. Background workers handle the tasks like async asset loading or AI computation. When profiling check for tasks that take too long, idle threads that could be used more efficiently, and whether you are actually utilizing enough concurrent threads. Let's take a closer look at the performance analysis of our worker thread. For example, when analyzing the performance of the game thread, if the game thread itself occupies most of the frame, then the game thread is the bottleneck. However, if the game thread is waiting for tasks, as shown in this figure, we need to pay attention to other threads as well. What task is this game thread waiting for? In such a case, select an event near the wait event. Then you can build the task dependency as shown in the figure. The selected event is the one that will be called next to the wait event on the game thread. But this event will wait for the pink arrow to complete before moving. This means that the game thread is waiting for this process to complete. Now, let's select the task waiting for processing to see the details of this process. You can see that this processing is done in the worker thread running behind the game thread, and that the physics update processing is being performed. In this figure, the game thread is not the bottleneck, so there is no problem. But it is important to understand that asynchronous processing like this can wait. Here's another example, this time with the render thread. We can see it blocked while waiting for a task. Again, the underlying issue is likely in another thread. Let's explore what that thread is doing. When we click on the blocked section, we can see that the render thread is waiting for several tasks to finish. This occurs before render graph builder step. All builder tasks need to be completed first. If we want to optimize this, we look at speeding up those async builder operations. We highlight one of these earliest dependency tasks. By tracking its timing, we can see when that async job began. Asynchronous work like this is common, and understanding when and where it starts is key to performance analysis. Here's a simplified timeline. Notice that during the frame 12, the worker thread is busy, while the game thread is relatively short. That suggests a heavy task is running on the worker thread and driving the frame and the frame time overall. In this kind of situation, the solution lies in optimizing the worker thread. Comparing thread timeline lets you clearly identify where the real bottleneck is happening. Of course, the real project involved more than just the games and the worker thread. The render and the RJ threads also depending on worker threads. So effectively performance work means understanding how these threads interact. In connection with worker thread, a few words about context switch tracing are in order. When thread switching frequently, CPU incurs extra overhead due to the need to save and restore state. Context switch tracing can be used to analyze such cases. To correctly analyze context switch, use the context switch channel. Context switch is CPU saving the state context of the currently running thread and switching to another thread. Therefore, if there are too many short-lived threads, context switching may occur excessively, causing worker thread or game thread to block other threads. Reading these reasons why threads are stacked is extremely important to utilizing insights. This graph shows which cores were running, which threads over time. If one core is dominated by a single thread, it may be blocked others. If switching is excessive, that's another red flag. Check whether your CPU usage is actually balanced and efficient. Now let's move on to our second major topic, file I/O. File access bottlenecks often show up during loading up screens or streaming heavy sections of the game. To analyze file I/O bottlenecks, we recommend using these commands. This setup helps you detect the performance issues caused by things like blocking I/O codes during gameplay or wrong stalls in the async loading thread. These problems often occur during map loading or game save load operations. As a point to remember, the game thread does not direct file access in asset loading. It issues an I/O request, which is handled by a dedicated file I/O thread. Therefore, when investigating I/O delays, check to see which thread accessed the file and if it is too long for large asset loads. Let's take a look at how file I/O appeared in Unreal Insight. This timeline comes from the Asset Loading Insight view and it shows actual I/O activity during the capture session. Each track here gives you a visual reference for where file reads happened and which thread or subsystem handled them. By analyzing this view, we can pinpoint the exact moment and location of a file I/O bottleneck. If you are investigating asset loading performance, enabling the loading track is very useful. It lets you see which asset was processed and how long each stage of loading took. For lower level analysis, you should enable the I/O activity and I/O store track. I/O activity shows which files were accessed, and I/O store activity shows chunk level read data. Together, they help determine whether your file access patterns are efficient or not. Asset loading insight also includes statistics about each package. This includes the total processing time per package and break down the specific to serialization. It's a great way to spot problematic packages quickly. Here's a simplified diagram of how asset load requests are issued and fulfilled. It starts with a request from the game thread, flows through async loading, then into the I/O system, and finally the physical file. This helps clarify the file I/O flow from request to read. Once loading is complete, the data returns to the game thread for deserialization and initialization. At the same time, we record asset activity in the loading track. This presents the full asset loading cycle. Once complete, the asset is ready for gameplay use. When optimization is needed in such as asset loading process, we believe there are three key points. First, improve blocking process such as deserialization. Second, reduce wait time. This could mean avoiding large file reads or changing the timing of asset loads. Third, optimize the file access itself, such as adjusting asset layout or chunking size. These steps go a long way in improving file I/O performance overall. To wrap up this section, here are the key takeaways for task graph. Pay attention to whether threads are being used efficiently. For file I/O, analyze the performance by paying attention to whether the streaming is controlled by preventing blocking, and access concentration among threads. There's the things that stat unit command alone cannot tell you, and the best part of this chapter is that you can use Unreal Insight to see the structure of code and effect. Okay, so let's move into the final section, best practice and my mistake. Now that we've covered the analysis techniques, we wrap up by discussing how to apply them and what kind of mindset is helpful when working on optimization. Let's start with a quick recap of what we've covered. We use stat unit to detect the surface level symptoms. Then perform the detailed analysis with Unreal Insight to drill down from high level observation to low level root causes. And so with repeated measurement and validation, we worked toward effective optimization. This might sound like a familiar workflow, but in this talk, I hope the example gave you a concrete sense of how to apply it in practice. When it comes to performance tuning, there are four key principles to keep in mind. First, always start with data. Don't guess. Measure. Second, avoid assumption. Trust your tool instead of gut feeling. Third, prioritize what matters most. Focus on high impact bottlenecks first. And finally, verify your changes. Always retest after each adjustment. The mindset you want is, what might I be missing? That attitude is what leads to meaningful improvement. Here are some concrete optimization guidelines. Design your system to do as little as possible. Keep things simple. If you can't avoid processing, keep it short and fast. When editing your new system, think, can this be parallelized? Can it be pulled or reused? Can its priority be managed with something like the significant manager? The consistent goal should always be to minimize processing wherever you can. Before we close, I want to point you to a few helpful resources. You don't need to memorize every detail. What's more important is knowing where to look when you need answers. And that brings us to the end of this talk. I hope this session has given you a solid first step toward using Unreal Insight to create faster, more stable game experiences. So thank you for listening.